Hi everyone, welcome to our video presentation. Have you ever wondered what is ultraviolet catastrophe that can spark into quantum revolution? In this video, we want to explain more about the idea of this revolution that's supported by the Rayleigh-Jeans law, Planck's quantum, impact and application of the ultraviolet catastrophe. Our group name is Ultraviolet Rebellion, and my name is Nurul Ain. With my fellow friends are Nur Syuhada Putri, Intan Sakinah, and Fiona. Before we go further, I want to explain about the understanding ultraviolet catastrophe. Ultraviolet catastrophe actually a failure in classical physics regarding the prediction in classical theory of blackbody radiation. In the late 19th century, physicists attempted to derive a mathematical formula to describe the spectrum of radiation emitted by a blackbody. The ideal blackbody would emit infinite energy at ultraviolet wavelength. This contradiction exposed the insufficiencies of classical theory, example, Rayleigh-Jeans law, and Max Planck introduced the concept of quantized energy level and solved the regarding issue leading to the formula of Planck's law. Rayleigh-Jeans law predicts the energy emitted by a blackbody can increase as wavelength decrease in classical physics. The formula was accurate at low frequency, which is long wavelength, but it is failed at high frequency at the short wavelength. This failure proved the limitation of classical physics in atomic and subatomic phenomena. The assumption is from application of classical principle, which are electromagnetic radiation is considered to behave like wave. The energy emitted is continuously. The equipartition theorem applied to all frequencies. After that, in Planck's resolution, Max Planck resolved this issue by proposing that electromagnetic energy could only be emitted or absorbed, which led to the Planck's law. The energy is quantized, discrete rather than continuous. Max Planck also said that energy of each quantum is proportional to the frequency. Planck's law matched experimental results across wavelengths that shown in the graph. The resolution of the ultraviolet catastrophe not only validated to Planck's idea but developed more in quantum physics.
So right now, I'm going to talk about the Rayleigh-Jeans law. Rayleigh-Jeans law in the ultraviolet catastrophe give a definition to describe the distribution of radiation emitted by a black body at higher temperature. The law can be expressed as stated in the slide. I symbolize for the spectral radiance, lambda symbolize for the wavelength, C symbolize for the speed of light, K symbolize for the Boltzmann constant, and P symbolize for the temperature. The next one is about application of Rayleigh-Jeans law. The first one is about blackbody radiation at higher temperature, for example, sun radiation. The second one is spectral distribution of light, for example, long wavelength behavior. In that slide, I already put some graph that show us about Rayleigh-Jeans law graph and the radiation graph. The graph is plotted energy density versus wavelength. However, in Rayleigh-Jeans law, there are also some limitations. The first one is about ultraviolet catastrophe, which is lead to unphysical prediction of infinite energy at short wavelength or higher frequency, but it can be resolved by using Planck's law. The second limitation is about breakdown at short wavelength, because it success at long wavelength in the infrared region, but it failed at short wavelength, which is in the ultraviolet region. Last but not least, I'm going to talk about the comparison of Rayleigh-Jeans law and Planck's law. Rayleigh-Jeans law predict infinite radiation at short wavelength. It also provides a linear relationship between the intensity and the temperature. However, the Planck's law correctly predicts the intensity across all wavelengths, and it also accounts for the quantization of energy level. Rayleigh-Jeans law can be used in many sectors. For example, in the sector of infrared spectroscopy, because Rayleigh's law is a method used to estimate the intensity of infrared radiation. And the second one, Rayleigh's law also can be used in the sector of astronomical observation.
Hello everyone, my name is Fiona. So for my part, I will present what is the Planck constant hypothesis. So that is the energy is not emitted or absorbed continuously. It is emitted or absorbed in the form of the wave packet or quantum. In this case, of the light of the quantum of the energy is often called photon. Next, we can see what is the formula that related with the quantum. So the amount of the energy associated with the quantum of radiation is directly proportional to the frequency of radiation. So we can see that the hash is represent the Planck constant. And then with our body can emit or absorb energy only in terms of integer, multiple of a quantum or photon. So we can see that the n is represent the integer which is 1, 2, 3, 4, 5, and so on. Therefore, the Max Planck explained the black body radiation in 1900 by assuming that the energy of the oscillation of the energy responsible for the radiation must be proportional to the integral multiple of the frequency. However, we can see that the formula E equals to NHV, where N is the integral, H is the Planck constant. The breadth found E comes in card with V, and the packet of the HV are called quantum. However, the Planck assumption leads to the correct form of the spectral function for a black body. You can see this is the formula for this assumption. So let's we take an example. If we now take the limit for the wavelength equals to 0, it is easy to prove that B goes to 0. In agreement with the experimental result, the plan also that can found that the experimental data could be reproduced exactly. Nevertheless, the brain could not offer a good justification for his assumption of the energy quantization. Now, physicists did not take this energy quantization idea seriously until Einstein involved a similar assumption to explain the photoelectric effect. In this page, you can see that is the graph intensity of the black body radiation versus frequency. There is the rainbow color in that from the red, the orange, yellow, and so on. However, that we know the hot object emit light will from the red color, yellow to the white. The black body absorbs all the radiation falling on it so that any light observed is being emitted. Therefore, as we know, the electromagnetic wave theory predicted that the object would emit radiation, but did not accurately predict the observed spectrum of the light at higher frequency, which is the ultraviolet catastrophe. Moreover, in the basic logic and the normal definition is that the chain interaction E exponent in the equation. That is the intensity of the light being produced at each wavelength based upon the comparison to the Bose-Boltzmann constant and the temperature. In the below, that is the red line going to the infinity. However, the actual result at each temperature is the Planck equation line, which is the blue, green, and red at the low wavelengths. At the normal wavelength, the curves are indistinguishable. The black and others all match as if the same. That the result diverges and instead of going to the infinity goes to 0. It is ultraviolet UV range of wavelength in the graphic below catastrophe. Further, all the Planck equation curves go back to the 0 and very smoothest energy. Lastly, the quantum equation do well to explain the slope line to the pit, but the instead explain that the quantum methods fail to explain the drop to 0.
So my name is Shuada. I'm going to talk about impacts of ultraviolet catastrophe. The application of Rayleigh-Jean's law to the radiation emitted by a black substance at high temperature gave rise to an issue in classical physics known as the ultraviolet catastrophe. This problem had a significant effect on the evaluation of contemporary physics, resulting in several groundbreaking theories and applications, most notably the development of quantum mechanics and the notion of quantized energy levels. There are three uh, impacts, which is foundation of quantum mechanics, mechanics of quantum development, and effect of statistical mechanics and thermodynamics. So the first one, when the ultraviolet disaster revealed the shortcomings of classical physics, Max Planck came up with the idea that energy is quantized. This paved the way for the groundbreaking discovery of quantum mechanics, which fundamentally altered our perception of the atomic and subatomic realms. For example, the Planck constant. So next, the second one is the mechanics of quantum development. So quantum mechanics was directly influenced by Planck's effort to address the ultraviolet disaster. His theories were expanded upon by later discoveries made by other scientists. So the first one, a direct extension of Planck's theories, Albert Einstein proposed that light is made up of quantized energy packets called photons in order to explain the photoelectric effect. So the Paul Dirac, Werner Heisenberg, and Erwin Schrödinger advanced the field of quantum mechanics, resulting in the complete theory that describes how subatomic particles behave. So the next one is the effect. So the development of statistical mechanics was also significantly influenced by the UV disaster. The statistical mechanics of equilibrium system was re-examined when black body radiation was not explained by classical physics. So in this graph, this shows the black body radiation. So the blue one is the highest wavelength here. So the application of ultraviolet catastrophe have both semiconductors, spectroscopy, nuclear physics, and black hole thermodynamics. So semiconductor technology uh, are devices such as transistor and lasers was directly impacted by the introduction of quantum physics. So the second one is spectroscopy. The quantization of energy levels improved the field of spectroscopy and provided an explanation for atomic spectra. So the third one is nuclear physics. The foundation for the development of nuclear power and technologies was laid by the understanding of nuclear process and the behavior of subatomic particles brought by the advancement of quantum mechanics, such as electron, proton, nucleons, and lastly, the black hole thermodynamics. Black hole thermodynamics and black hole radiation, Hawking radiation are studied using quantum theory based on ideas like temperature and entropy. So the conclusion is, in the history of physics, the ultraviolet disaster was a turning point. Our knowledge of energy, matter, and the physical world has been drastically altered by the quantum theory, which was developed in response to classical physics' inability to explain black-body radiation. The knowledge gathered from resolving the disaster has had a profound impact on the creation of technology ranging from semiconductors to lasers, and it has even laid the groundwork for our current understanding of thermodynamics and quantum physics. This physics episode emphasized how crucial is it to update outdated theories in the face of experimental inconsistencies, a process that propels scientific advance. So, thank you.